Hello, Physics 2B, Section 7. We're on the last week of the magnetism unit, the week with all the exams, practice and actualized. There's a few things that appear a little differently on the Tuesday, such as now a first practice test is posted. Okay. Additionally, in front of it, there's also a PDF of the equation page. Okay. The idea behind that is if you are so inclined, you can print that out so that you don't need to scroll up and down as much during the exam, so that you have, so you can actually have the equation page with you as a physical thing. Okay. And one more thing, the lecture video, which you're watching right now. All right. Thursday, we have midterm 2. As such, I'm going to have it set so that I expect people to complete it in the morning, but I do understand that there are people that, since it's the asynchronous section, won't be able to take it till the afternoon. Just send me an email if that's the case for you, so that I know not to worry that you've forgotten or something like that. Okay, so during AM. Okay, email if otherwise. All right. And that's the end of that unit. When we move on to week 12, we'll be looking at traveling light, specifically about how light moves through different mediums. Okay. There's a whole bunch of material available, so you can get a jump on it, all posted in this part of the homepage. But for now, I expect that everyone's just focused on the exam. So once you're done with the exam, you might want to start switching gears for this last unit. There we go. That's the administrative stuff. Looking forward. You've had the weekend to work on the second unit practice test, and that's what I'm going to go over today. Okay. I'm not going to make a solution set for the other practice test. That one you should do and see how well you can do without any external prompting. That usually improves outcomes if you practice without already knowing answers. A note about part of the equation sheet that would be definitely worth focusing on more than the others. We have all of this section available on what's going on with AC circuits. And we have all of this section on other parts that are all magnetism. Okay. So that's parts that people usually need to focus on, in addition to the permeability constant up there. All right. Jumping right into it. Question 1. True or false? Using a diamagnetic superconductor, is it possible to create a magnetic levitation train that works upside down? This one actually comes from this question comes from one of the videos that I posted, that I shared. That's the mag train video. Where you had the guy from Oxford talking about magnetic levitation, and he set up this little track and found different ways that a little bit of ceramic could be cooled into becoming a superconductor, and to see if he could make a magnetic train. And he was successful, and specifically because it was a diamagnetic material, what he called a magnetic mirror. And then while he's talking about that, he flips the track upside down and shows that it actually can work upside down as well. So true. Number 2. There is a current I flowing in a clockwise direction in a square loop of wire that is in the plane of the paper. If the magnetic field B is out of the paper and through the loop perfectly, and if each side of the loop has length L, then the net torque acting on the loop is, well, first off, I want to note that we're talking about torque. Not force, but torque. So whatever we use should have units of torque. Okay? Remember, torque is a force multiplied by a moment arm. They have to be all perpendicular. 0. 0 can be a torque, so that's fine. 2 ILB. Well, ILB is, or IBL, is the magnetic force. So this one has units of force. So it cannot be that one. And for ILB, same issue, units of force. Finally, the last one is IBL times L. Therefore, this one actually does have units of torque. So we've got 2 possibilities now. We've got the answer is either 0 or IBL squared. Which is it? Well, let's look to see what the forces tell us about what's going on with the torque. On the left-hand side, using my right-hand rule for forces, fingers up the page, palm out of the page, so I'm just looking at my palm on that one. I end up with a force to the right. On the top, fingers to the right, palm out of the page, I end up with my palm pointing down the screen. On the right-hand side, fingers down the screen, palm towards me, thumb is pointing to the left, and this last one is also inwards. All 4 of these forces point towards the center of mass. When the force points towards the center of mass, it does not apply any torque. So our answer there is no torque. So that's one way that we can get to an answer of 0 torque. Here's another way. The other way is to remember something about magnetic moments. Okay? Versus magnetic fields external. The loop itself of wire has current flowing like so. Using the source's right-hand rule, you can find the direction of the magnetic moment of the loop. And the magnetic moment of the loop is going to be into the page. I get that by putting my fingers around in that green loop, and I end up with my thumb pointing into the page. B external, on the other hand, is out of the page. This means that the 2 of them are aligned. Okay? They are parallel with each other. And you might say, well, they're not exactly parallel. Well, any situation where you have one thing in one direction and the other thing in the opposite direction perfectly, and I did use the term perfectly there, then that's parallel. Sometimes it's called anti-parallel, but it's parallel. The big point is that no part of it is perpendicular. Okay? So if you think of that magnetic moment as a compass, it's already aligned with the external magnetic field. Therefore, it will not be rotated. Therefore, zero torque. Conversely, different situation. If I had the same loop with the same current, and I had the magnetic field pointing across it, not through it, in that case, the magnetic moment of the loop, still being into the page, is perpendicular to the magnetic field pointing to the right. When they're perpendicular like that, it'll be the magnetic moment times the magnetic field, which is going to be I L squared times B times the sine of 90, which is 1. So in this situation, that's when you actually get IBL squared. But when they're aligned, no torque. Do consider different variations on this problem. Like, what if I made this a force problem? What if I changed this to a different orientation of different parts? That's something I like to do on my exams, just tweak the question a little bit. Question 3. 2 insulated current-carrying straight wires of equal length are arranged in the lab so that wire A and wire B carry current in the opposite direction. So it's the current of A, and the current of B is in the opposite direction. The wires are separated by a distance d, but they run parallel along their entire length. Which of the following statements is true? My statements: attract, repel, forces, 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 torque. It looks like I should at least start by doing a statement of what's going on with the forces between them, and then maybe I'll need to talk about torque. Let's take a look. In order to see how they interact force-wise, I need to find out what magnetic field they both create. A creates a magnetic field that is into the page over here. Whereas B, using the source's right-hand rule, creates a magnetic field that's into the page over here. Zooming in on them individually. Using the force's right-hand rule, I got my current down the page. I've got the magnetic field that's into the page. So I end up with the force of A on B pointing to the right with my thumb. Conversely, current up the page, magnetic field into the page, I end up with my thumb pointing to the left. So that's the direction of the force of B on A. Looking at these two forces, how they're pointing in the opposite direction, and more so how they are pointing outwards from their mutual center, tells me that the two wires are repelling each other. So that's our answer. Number 4. Soft iron has atoms that can rotate independently. Okay, so looking at that, soft iron has an atom here, an atom here, and an atom here, and they can individually rotate what's happening with them magnetically. Hard iron is more rigid, and large clumps of the iron rotate together. So that'd be all of these guys, and as a group, they rotate together. Which one is the better material to use for an inexpensive compass? Well, soft iron. Soft iron should be used for a magnetic coupler, because you do not want the coupler to move. You just want it to stay inside of one region and the other part in another region. You don't want it rotating through different things or making anything twist around. So you just want the atoms to rotate. An example of this is a transformer. Hard iron, that's going to have an entire object rotating together, which is exactly what compasses do. Okay, the entire compass rotates in the magnetic field. Hard iron. Okay. And neither of the last two are even partially correct. All right. That brings us to number 5. Weird thing about number 5 is that it looks a lot like number 6. The resistor's voltage in an AC RLC circuit. The resistor's voltage in an AC RLC circuit. Very, very similar questions. So similar that it's, you think, hey, he just did the same question twice. I did, but I gave different answers. Voltage, 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 current, 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 current. Okay, so I'm looking at the same question in 2 different ways. All right. So I'm going to start by drawing a phasor diagram. Voltage for a resistor, voltage for an inductor, voltage for a capacitor, and then the voltage for the power supply is off like so. Additionally, the direction for the current is same direction as the resistor. Okay. We've got 90 degrees here, 90 degrees here. We have some angle phi here. What's that angle phi? That angle phi is equal to the inverse tangent of chi sub L minus chi sub C over R. Remembering that chi sub L minus chi sub C is 2 pi F L minus 1 over 2 pi F C. That's what our numerator looks like. Okay. So, the resistor's voltage in an AC RLC circuit leads the input voltage by 90 degrees? No. It's at some angle phi. Lags the input voltage by 90 degrees? No. May lead or lag the input voltage depending on multiple factors? Yes. Those multiple factors are the frequency in the circuit, the inductance, and the capacitance. That's what will determine whether this is going to be positive or negative in the numerator, and exactly what our angle phi will be. There we go. 6. Resistor's voltage in an AC RLC circuit compared to the current. Well, you can see how I have them in the same direction over here, so that I'm going to jump directly to the answer. Is in phase with the current. That's what that means. There we go. I highly, highly, highly suggest drawing phasor diagrams when you're trying to come at these AC circuit problems. Okay, it gets all the information all in one spot. Number 7. A moving electron enters a magnetic field. Which way will the electron turn from our perspective? So it's asking what's the direction of the magnetic force. Okay. Note this. The magnetic force is always perpendicular to the velocity. As such, it cannot be left or right. Also, the magnetic force is always perpendicular to the magnetic field. So it cannot be into the page or out of the page. So it's either up the page or down the page. Let's do our right-hand rule. Fingers to the left for the velocity. Magnetic field out of the page. And my thumb will point up the page. That is the direction of the force magnetically if we're dealing with a positive charge. But we're not dealing with a positive charge. We're dealing with a negative charge. So that involves the rarely invoked Rule 4, where if you're dealing with a negative charge, flip your result. Boom. Down the page. And there you go. That's number 7. Number 8. A square circuit loop is moving into a magnetic field. Which direction will the induced current flow in the circuit? Induced. Since this is an induced problem, I need to think about this in a very specific way. Firstly, what is the initial direction of the magnetic field? What's the final direction of the magnetic field? And what's the change in the magnetic field? Once I have that, what is the direction of the response magnetic field? And what is the direction of the response current linked with that response magnetic field? From the top. Initially, it's out of the page. Coming towards you. But since we're getting more and more area, the more that this moves into the region, we're getting more and more magnetic field through that loop. Therefore, the change is more and more out of the page. Therefore, the response magnetic field is into the page. And I can use the source's right-hand rule to put my thumb into the screen, and my fingers will naturally loop around like so. Therefore, I'm getting clockwise. Since all of those arrows are pointing opposite of the direction of positive theta. Okay, just as a little reminder which one's which, because we have way too many digital clocks these days. We have clockwise and we have counterclockwise as our directionalities. Okay, this one is clockwise. That's number 8. Now number 9. Number 9 is the only purely numerical question on the entire exam. And There will be more than one on the actual exam, as a heads up. So for this one, an electron moving perpendicular to a uniform magnetic field of 0.22 Tesla moves in a circle with a speed of 1.5 times 10 to the 7 meters per second. What is the radius of the circle? Okay, this is a circular motion magnetic field problem involving an electron. Okay, whenever we have those, we need to consider the magnetic force in the situation. And we need to see how that force results in some sort of motion. And since it's circular motion, we have a centripetal acceleration to consider. Combining those three, I plug the force into the net force side and the acceleration into MA side. So I get QVB sine theta is equal to mv squared over r. I'm going to take that all the way down to the main part. All right. QVB sine theta is equal to mv squared over r. Since the movement is perpendicular to the magnetic field, sine of 90 degrees is equal to 1. We also have a speed on this side and a speed squared on this side, so I can cancel out one of the v's. And when I rewrite this, I get QB is equal to mv over r. I want to know the radius of the circle. Solving for r, I get mv over qb, which might be a memorizable answer, a memorizable equation, because I pointed out that we've got a 2b thing in the numerator, momentum, and in the denominator we have some physics 2b stuff, charges and magnetic fields. Take all this and plug in all of our numbers. The mass, provided like this, like so, 9.11 e negative 31. The speed, 1.5 e7. The charge is the charge of the electron, 1.6 e negative 19. And lastly, the magnetic field is 0.22 Tesla. Putting all that in the calculator gives me 3.88 e negative 4 meters for our radius. Well, how big is that? Well, remember that millimeters is 10 to the negative 3. Well, pulling out a 10 to the negative 3, I get 3.88 e negative 1 millimeters. In other words, 0.388 millimeters. So, which will round to this is our answer. There we go. I did this quickly because I've already done the calculation on my calculator, so I just did that, the calculator part, referenced what I'd done in my past. Last two questions, 10 and 11. Why can't a constant uniform magnetic field do work on a point particle? Okay, I got a few interesting answers in the other sections from this one, from people. I had people say, well, that's because the work is zero. But that's basically what the problem's already saying. It says it can't do work. So it's already saying that the work is equal to zero. It's not asking if the work is equal to zero, it's asking why is the work equal to zero. Okay, so we already know that the work is equal to zero. Okay, we also know that we're dealing with magnetic field problem. Okay, how are magnetic fields related to the work done? They're related via forces. Okay, so work done is equal to the force that is parallel to some motion multiplied by each other. Which means that you only have work done if the force is at all parallel to the motion. But when we have magnetic forces, we get motion that is like so. And we get, so that's our delta x, delta x, delta x. And we get forces that are always perpendicular to that. Therefore, the magnetic force is always perpendicular to the motion. Since the force is perpendicular, no part is parallel. Therefore, the work done is equal to zero. Putting it plainly, why can't a constant uniform magnetic field do work on a point particle? Because the magnetic force is always perpendicular to the charge motion. Period. All right. And there we go. This question does rely heavily on remembering information about Physics 2A, specifically this statement about work. Okay, that's just a course prerequisite that's expected to be known. Next, last question. How can a charged capacitor in a magnetic field be used to create a magnetic velocity selector? I'm going to draw a velocity selector. First off, my capacitor, which is going to have a positive side and a negative side. As such, it creates an electric field from high to low. The magnetic field, I want that to be into the page. So that when a positive charge is entering the region, it will experience two forces. Firstly, the electric force, Q times E, when you get positive multiplied by down. So I get down. Then there's the magnetic force using the forces right-hand rule. Magnetic velocities to the right, fingers to the right. Magnetic field is into the page, palm is into the page. And that leaves me with my thumb pointing up the page. That's the direction of the magnetic force, which is equal to QVB. B. Next, how is this a velocity selector? Well, when the forces balance, then I say QE is equal to QVB, Q's cancel, and that speed is equal to the electric field divided by the magnetic field. That is just right, as listed in the question. What does just right mean? Just right means it's going to continue moving undeflected with a net force of 0 on it. Next, if it is too fast. If it's too fast, then the magnetic force is going to get too big because it's dependent on the speed. So magnetic force is too big, which means it's going to deflect upwards. Okay, so that's going to be too fast. And then for too slow, the magnetic force is going to get small, and the electric field force stays the same. So in that case, the electric force will be the stronger one, and it will deflect like so. Okay, so it's a balance between the two forces. That's what a velocity selector is. So for the bottom one, the magnetic force was too small. Okay. It's a velocity selector because only a certain speed gets through. Therefore, only the charges moving at the right speed are going to make it through, and you have your particles all prepped and good to go. That is the end of it. Okay. Hopefully these explanations helped you. Do rewatch any part that you need further assistance on, or send me an email if you have further questions. Let me see. We've got do work on the other practice test. See if that can help you get ready for the exam. And make sure that you get a good night's sleep on Wednesday night so that you can be ready for the exam either in the morning or if you email me the afternoon. Okay. There we go. That's our preparation for the exam. Just a short 40-minute video today. I hope it helped you out. Good luck, and I'll talk to you more next week because there's no lecture video on exam days. So I'll see you in week 12.